Welcome to Chapter 4, Section 11, Rectilinear Motion. In this section, we're going to study the motion of a particle along a line and determine the attributes of a position versus time graph that yields velocity and acceleration. Now, before we get into that, let's talk about what we're dealing with rectilinear motion. Picture a particle along a line. So we just have some linear path, and we just have an object. It can be a particle, it can be a piston, it can be a person, whatever it is. They're moving along this linear path back and forth, and they might speed up in one section and slow down and then change directions, and the entire time their path is along a given line. All right. Now, when we look at the position functions, the functions themselves are not going to be linear. Just the path is linear. Okay, so we're going to look at functions that are going to tell us the position, but that is the position on that one-dimensional axis. Okay, why are we only dealing with one dimension? Because it's a lot simpler to start with. You'll get into 2 and 3 dimensions when you go into multivariable calculus, but in just regular calc, we only deal with one dimension. So we have a position function. We're going to call it S, and it's going to be a function of time. So S is going to depend on the independent variable t, that stands for time. And if we look at the derivative of time the derivative of position with respect to time, we get a velocity function. So the first derivative, S prime of t, is equal to our velocity function. And this is the instantaneous velocity. Okay? So first derivative is instantaneous velocity. Second derivative gives us the instantaneous acceleration. All right, and we're talking derivatives of the position function. So derivative of position gives us velocity, derivative of velocity gives us acceleration, or second derivative of position gives us acceleration. All right, so that's how those three are related, and we're going to treat those as such. So if we have a position function, want to find an acceleration function, take two derivatives, and we have it. So let's take a look at things graphically and describe the motion of a particle. So if this is the position versus time graph, now this is just telling us what is the position at any given time. So at this time right here, we have a position, a positive position, and typically we have a reference point that to the right is positive and to the left is negative. So when a position is positive, we are to the right of the origin. When a position is negative, we are to the left of the origin. So right here, this entire graph, the position is positive. So the entire time, our particle is to the right of the origin. Now, what else do we know about this? Well, on this graph, we have a general slope that is negative. So that means that our velocity is negative. Okay? So throughout this entire trip, our velocity is negative. What does that mean? That means we're moving to the left. So this particle starts to the right of the origin, but is moving to the left because velocity is negative. Well, what about its concavity? The concavity shows that it's concave down, so that means the acceleration is also negative. So this is a particle that starts to the right of the origin, is moving to the left, and its rate of change is also to the left. So it's moving to the left more each second than it was the second before. All right, and we're going to delve into that a little more in just a moment. Let's look at number 2 here. We have, once again, a positive function everywhere. S is positive, so that means that we are to the right of the origin, and we have an upward slope, so that means V is positive, and we have concave up, so that means that acceleration is positive. So this is a particle that starts to the right of the origin, is moving to the right, and the rate at which it's moving is increasing. All right, number 3. Well, it's a very similar situation. We are still moving to the right, and the rate at which we're moving to the right is increasing because the velocity is positive because we have a positive slope. Acceleration is positive because we're concave up. But the difference here is our starting point. In number 3, we're starting to the left of the origin because we're negative. And actually, by the time that our graph ends here, we are still to the left of the origin. Now, throughout our entire path, we are moving to the right, and we're increasing the rate at which we're moving to the right because our acceleration is positive. All right, but our position initially is to the left. Over here, number 4, once again, our position is to the left, but we're moving to the left because velocity is negative. All right, and what's our acceleration? We're concave down, so our acceleration is negative. Okay, now one thing you'll notice in all four of these examples, both the velocity and acceleration have the same sign. And when that happens, we say that the speed is increasing. Now, what is speed? Speed is the absolute value of the velocity. Speed is what you read on your speedometer when you're driving down the road. Velocity is two parts. It's a vector. It has both a quantity, a magnitude, and it has a direction. So when we say the velocity is -3, that means we're moving 3 to the left, all right, given whatever units we may be using at the time. But if velocity is -3, the speed of that particle at that point is 3. We don't care about the sign. Speed is just how fast are you going? So this is the important part. When acceleration and velocity are in the same direction or they have the same sign, we are increasing speed, or we say we are speeding up. When they are opposite signs, then we are decreasing our speed or we're slowing down. Okay, so in all these examples that we just had, we were speeding up because we're the same sign. So you might ask, well, what's the shape going to look like if we're slowing down? Well, what if we had a graph that looked like this? A positive general slope, so that means that we're moving to the right, but our concavity is down, so our acceleration is negative. So we are moving to the right, but the rate at which we're moving to the right is decreasing. Okay, so we're going to use these to describe the motion of particles, okay? And this should be the particle. I apologize, an E is missing there. So let's look at what's going on here. Well, if we look at this, this is our position versus time. So let's see, where is our slope 0? Well, our slope is 0 here, so let's call that A. Our slope is, actually, the slope here is undefined at B, but we'll say that that might be something significant in a second. And here, our slope is 0 at C. So when our slope is 0, then that means we have the potential to change directions. Okay, so what's happening here? From 0 to A, we have a positive slope. So velocity is positive. From 0 to A, we are moving to the right. We're moving to the right because we have a positive velocity. Where do we start? What's our starting position? Well, we're at the origin because S of 0 is 0. So we start at the origin. We're moving to the right. Now, let's talk about the rate at which we're moving to the right. Well, our concavity here is concave up, but it changes somewhere around here to, and let's call that D. So somewhere from 0 to D, we are concave up, or we have positive acceleration. But here we have negative acceleration because we're concave down. And that goes until some other point of inflection, we'll call it E, where our acceleration is also negative. But what are we talking about here from this point to, let's call this point F? From A all the way to F, we have a negative velocity, right? So from 0 to A, we have positive velocity. From A to F, we have negative velocity. Well, from F to B, we still have negative velocity. And then we look from B all the way up to, let's call this point G, all right? That's a positive velocity, and this is still a positive velocity. And over here we have a negative velocity. Okay, now how are we getting velocity? That's the slope of our position graph. The slope of our position graph tells us velocity. So from time equals 0 to A, we're moving to the right. Then we turn around and we move to the left. And we keep moving to the left all the way until time equals B, and we move back to the right. And our velocity is changing throughout this whole time, and then we get to time equals C, and we move back to the left. Okay, now let's finish talking about our acceleration. Well, we have acceleration positive here, acceleration negative here because we're concave down, and then we're concave up again here, so our acceleration is positive. But what's our concavity between F and G? Well, there is no concavity because this is a linear relationship, so acceleration is equal to 0 in both these regions here. Okay, and then we go back up to here, and we're going to have some point of inflection. Let's call that H, and then another point of inflection over here. We'll call that I. And so in this region, we're concave up, so we have a positive acceleration. That's going to be a negative acceleration in those two regions there because we're concave down, and then a positive acceleration. So if we want to identify at what regions or what intervals is this function speeding up, well, that's when the sign of acceleration and velocity are the same. So let's look. Well, we've got it right here. So that's from 0 to D. Okay, now not all the way to A because we change our concavity there. All right, so we're actually slowing down at that point. And then right here, we have it because that's negative velocity, negative acceleration. So from A to E, and then we're coming down here, negative, negative. Oh, wait, acceleration 0, so well, we're not speeding up. There is no acceleration. And then over here, we have positive velocity, positive acceleration, so G to H. And then over here, this is negative, and this is negative, negative. So both the velocity and acceleration is negative from, what is that? That is from C to I. We are also speeding up. Okay, so these are the 4 intervals in which we are speeding up, meaning we are increasing the rate at which we're moving. Now, that by saying speeding up, that tells us nothing about the direction we're going. It just tells us that the speed is increasing. Okay, and then those other intervals, excluding F to G, we are slowing down because our signs are opposite. All right, now I know there's a lot here, a lot of information going on here, looking at our aspects of both the first derivative, second derivative. But remember, first derivative of a graph tells us the slope of a graph tells us the first derivative. So when we have a position graph, the slope of that graph tells us about the velocity. The concavity of that graph tells us about the acceleration. Now, if this were a velocity graph, then the slope would tell us about the acceleration. The concavity would actually give us something called jerk, which we're not going to talk about in this class, and we're not going to even go down that road. But the aspect of a velocity graph that gives us position is something that we're going to have to talk about next section of this course when we get into integration. All right, what I want you to do is I want you to try a couple problems from the book on page 315. You don't need to do all of 1 to 9, but I'd like to see you pick maybe 3 problems from 1 to 9 in page 315 from the book, and then bring that into class tomorrow, and we'll talk about any issues you have.